Calculus is hard, but calculus is also useful. Today, I'll be showing you one of the uses of differentiation in order to find the fastest way to do something. Imagine a situation where you have to travel from one point to another. However, the speed at which you can travel between those 2 points are not constant throughout. A very real situation is, say, you're trying to get across a river to a point that is on the other side of a river, some distance downstream or upstream. There are many ways to cross the river. You can swim straight across and then run the rest of the way, or you can swim all the way to your destination. Both of these methods will get you to where you want to be, but each method would take a different amount of time, since your speed when you're swimming and your speed when you're running is different. What you can do with differentiation is find out the quickest way to do this. Let's use a river example. Say the river is 5 kilometers wide and your destination is 10 kilometers downstream. You know you can swim at a constant 5 kilometers per hour and you can run at 10 kilometers per hour. What should be your route to make the trip as fast as possible? Before we begin our calculations, first we need to keep in mind that time elapsed, speed, and distance are related by distance equals to velocity times time. Since we're finding the fastest route, we rearrange the formula to express time. Since we already know the velocity both in the water and on land, all we need is to find the distance over water and over land to complete our equation of time. Let's draw a diagram. We'll calculate the distance traveled over water with Pythagoras' theorem, substituting this side with x. This would allow us to find the distance traveled over land as well. Since we know that time equals the distance over velocity, we divide our distances with their respective velocities, giving us two equations for time taken on the water and on land. By adding the two functions together, you get the total time for the trip. This is what we're trying to minimize. By finding the first derivative, then setting the equation equal to 0 and solving for x, we can find the critical number which represents our extrema. We then substitute the critical number and the endpoints into our equation for time to find the minimum. Keep in mind that since our destination is 10 kilometers away, our endpoints are from 0 to 10. We can confirm our answers by looking at graphs of the equation as well. If we graph our equation for time from x equals to 0 to x equals to 10, we will see that the graph's lowest point is at x equals to 2.887, which is consistent with what we first found. This is the minimum, where the slope is 0. To confirm this even more, we can graph the first derivative. The graph of the first derivative crosses the x-axis at the same x value, confirming that the point is indeed the minimum. From all this, we can conclude that to make the trip in as little time as possible, you should swim to this point, which is 2.887 kilometers from point C, then run the rest of the way. This method can be adapted to fit other situations as well. For example, you can find the fastest location to connect between two flights, or find the fastest route to travel from your house to school if you take the BTS, then the motorbike from the station. As velocities in a situation change, your fastest route would change as well. In my river crossing example, if the current changes, my swimming speed would change, and as a result, I would have to change the point of landing up or downstream. This is one of the many uses of differentiation.